Next, we shall see how to write the formula of the complex compound if the IUPAC name is given. For example, consider the first one. The IUPAC name of the compound is given to be tetraamine aqua chlorido cobalt 3 chloride. From the name, it is clear that 4 ammonia molecules are present as ligands, water molecule is present as ligand, and chlorido is also present as ligand. Cobalt 3 shows that the oxidation number of cobalt is +3. Cobalt 3 chloride. Chloride means chlorine is present outside the coordination sphere. So knowing the oxidation number of cobalt and the ligands, we can get the final formula as CONH3 4 times H2OCl Cl2. Now consider potassium tetrahydroxidozincate 2. Here potassium is present as counter ion. 4 OH groups are present. Zincate shows that the complex ion present is anion. The oxidation number of zinc is +2. So we get the formula as K2ZnOH 4 times. Consider the third example, dichlorido bisethane 1,2-diamine cobalt 3. The oxidation number of cobalt is +3. 2 chloride ions are present as ligands and 2 En groups are present. Therefore, we can get the formula as COCl2 En twice plus. Tetracarbonyl nickel 0. 4 CO groups are present. The central metal atom is nickel. The oxidation state of nickel is 0. So we get the formula as NiCO 4 times. Next, we shall learn about valence bond theory, which is used to explain the shape of complex compounds. Consider the first example, CONH3 6 times 3 plus. The atomic number of cobalt is 27 and the electronic configuration can be written as argon 4s2 3d7. In this complex ion, cobalt is under +3 oxidation state. Therefore, the configuration of cobalt 3 plus can be written as 3d6. Orbitals of cobalt 3 plus is shown. We can find 6 electrons present in the 3d orbitals. 4s is vacant and 4p is also vacant. Ammonia is a strong ligand, so electron pairing will take place. As a result of electron pairing in the 3d orbitals, 3 of the 3d orbitals will be now containing paired electrons, which makes available 2 empty 3d orbitals. So those 2 empty 3d orbitals along with 1 4s and 3 4p orbitals will mix together to give 6 d2sp3 hybrid orbitals. Therefore, cobalt 3 plus is under d2sp3 hybridized state. 6 d2sp3 hybrid orbitals will be now available with cobalt 3 plus, the central metal ion. Now consider the complex ion CONH3 6 times 3 plus. The 3d orbitals which are not involved in hybridization with paired electrons can be shown, and next to that we can show that all the d2sp3 hybrid orbitals of cobalt 3 plus will be now filled by electrons because 6 pairs of electrons will come from 6 ammonia molecules. So cobalt 3 plus is under d2sp3 hybridized state, therefore it is an octahedral complex. Since there are no unpaired electrons, the complex is diamagnetic, and it is known as an inner orbital complex because the inner 3d orbitals are involved in hybridization. Since unpaired electrons are not present, it is a low spin complex. It can also be called as spin paired complex. Next, consider COF63 minus. The oxidation state of cobalt is +3, therefore the configuration will be 3d6. Orbitals of cobalt 3 plus ion is shown. 6 electrons are present in the 3d orbitals. 4s, 4p and 4d orbitals will be vacant. Fluoride ion is a weak ligand, therefore electron pairing will not take place. Therefore the 3d orbitals cannot be used for hybridization. Hence 1 4s and 3 4p and 2 4d orbitals will mix together to give 6 sp3d2 hybrid orbitals. Therefore cobalt 3 plus is under sp3d2 hybridization. The 6 electrons in the 3d orbitals are shown, and then we can show empty sp3d2 hybrid orbitals available with cobalt 3 plus. The hybrid orbitals will be vacant. Now when it forms the complex ion COF63 minus, the 6 sp3d2 hybrid orbitals will be filled because of the presence of 6 fluoride ions. 6 fluoride ions will donate 6 pairs of electrons. The filling of the sp3d2 hybrid orbitals can be shown. by the 6 pairs of electrons from 6 fluoride ions. Now consider 3d6 configuration. There we can find 4 unpaired electrons. So due to the presence of 4 unpaired electrons, the complex will be paramagnetic. The state of hybridization is sp3d2, therefore the complex is octahedral. It is known as outer orbital complex because the outer 4d orbitals are involved in hybridization. Since it is paramagnetic, due to the presence of unpaired electrons, the complex can be considered as high spin or spin-free complex. Next example, NiCl4 2-. Atomic number of nickel is 28, so the configuration can be written as argon configuration 4s2 3d8. The oxidation number of nickel in this complex ion is 2+. Therefore, the configuration of nickel 2+ can be written as 3d8. Orbitals of nickel 2+ ion is shown. 8 electrons in the 3d orbitals, 4s and 4p will be vacant. Chloride is a weak ligand, so electron pairing will not take place. 4 chloride ions are bound to nickel. So there should be 4 hybrid orbitals available with nickel. Therefore, 1 4s and 3 4p orbitals will mix together to give 4 sp3 hybrid orbitals. Therefore, nickel is under sp3 hybridized state. 3d8 configuration is shown. Along with that, 4 empty sp3 hybrid orbitals are also shown. In NiCl4 2-, the 3d8 configuration is shown, and then there will be 4 pairs of electrons from 4 chloride ions present in the sp3 hybrid orbitals. So nickel 2+ is under sp3 hybridized state, therefore the complex is tetrahedral. Due to the presence of 2 unpaired electrons in the 3d orbitals, the complex is paramagnetic, and it can also be called as high spin complex. Consider the next complex compound, tetracarbonyl nickel 0. Here in this compound, nickel exists as nickel atom and not as ion. Atomic number of nickel is 28. The configuration is written as argon 4s2 3d8. The configuration of nickel atom will be 3d8 4s2. Orbitals of nickel shown 3d with 8 electrons. 2 electrons in the 4s and 4p orbitals will be vacant. Carbon monoxide is a strong ligand, therefore electron pairing will take place. 2 of the 4s electrons will be transferred to the 3d orbitals and thus pairing takes place. 4s and the 4p orbitals will be now vacant. 1 4s will mix with 3 4p orbitals to give 4 sp3 hybrid orbitals. 3d10 configuration of nickel is shown. Along with that, 4 empty sp3 hybrid orbitals are also shown. Now take the complex NiCO4 times. The 3d configuration is shown with 10 electrons, and there will be 4 pairs of electrons in the sp3 hybrid orbitals coming from the 4 carbon monoxide molecules. Consider the 3d configuration. No unpaired electrons are present, therefore the complex is diamagnetic. And since it is sp3 hybridization, the complex will be tetrahedral. Consider the next example, NiCN4 times 2-. Nickel atomic number 28, electronic configuration can be written as argon 4s2 3d8. Here nickel exists as nickel ion Ni2+. The configuration is 3d8. Orbitals of nickel 2+, 8 electrons are shown in 3d orbitals, 4 is vacant and 4p is also vacant. Cn- is a strong ligand, therefore electron pairing will take place. As a result of electron pairing, one 3d orbital will be available, so that empty 3d orbital along with 1 4s and 2 4p orbitals will mix together to give 4 dsp2 hybrid orbitals. Therefore nickel 2+ is under dsp2 hybridization. The 3d configuration is shown with 8 electrons. Empty dsp2 hybrid orbitals are also shown. Now consider NiCN4 times 2-. 8 electrons are present in the 3d orbitals, and 4 pairs of electrons will now come from 4 Cn- ions, and dsp2 hybrid orbitals will be now filled with electron pairs. Since nickel is under dsp2 hybridization, the complex is square planar, and there are no unpaired electrons in the 3d orbitals. Therefore the complex is diamagnetic.